So in section 3.3, we looked at something called the first derivative test. And we talked about using the first derivative to talk about increasing and decreasing and whether things are maximums or minimums. Today we're going to talk about concavity. It's something you've heard of before. We haven't done a lot with it ourselves in this class, but we will explore it today. And then we're going to talk about the second derivative test, which obviously means we're going to be taking second derivatives. So to start with, concavity. So for a function f that is differentiable on an interval I, the graph of f is concave up if the derivative is increasing, and it is concave down if the derivative is decreasing. So if something is increasing, what we found out in the last section is that its derivative is positive, right? An increasing graph has a positive derivative, and a decreasing graph has a negative derivative. So this idea of the derivative itself, here, f prime, increasing or decreasing, will connect to those ideas of positive and negative that we saw in the last section. And that's actually what our test for concavity, the next one, is talking about. It's talking about how those connect back to what we just did in the previous section. So our test for concavity takes it a step further. Instead of relating it to the derivative being increasing or the derivative being decreasing, we take a derivative of the derivative. And the derivative of the derivative is otherwise known as the second derivative. So we see the same descriptive phrases here, except instead of it talking about derivative, it's talking about second derivative. And instead of talking about increasing and decreasing, it talks about it being positive or negative. Okay? So if the second derivative is positive, we have a graph that's concave up. And if the second derivative is negative, then the graph, or the portion of that graph, if that's what's happening, is concave down. Okay? So, in very much the same way that we were determining whether things were increasing and decreasing by taking derivatives and setting them equal to 0 and making sign charts, we can do the same sort of thing for finding if things are concave up and concave down. But instead of taking the derivative, we take the derivative of the derivative, or the second derivative, set it equal to 0 and create a sign chart. So, we're going to do that. We're going to start with something that's really nice and simple to take derivatives of, very clean, polynomial. So we're supposed to be determining the intervals where it's concave up and concave down. So anytime you see questions about concavity, you should immediately think, I need a second derivative. Okay? It's like a red flag thing. Concave up, concave down, second derivative. So we're going to take the derivative first. So what is the derivative of x to the fourth minus 6x squared plus 2x plus 3? Okay, everybody good with that? That works, right? Okay. But we're not asking about increasing or decreasing. If we were, we would stop here. We'd set it equal to 0. We'd make our sign chart just like in section 3.3. But we're looking at concavity now, so we need a second derivative. So we're going to do it again. So what's the derivative of 4x cubed minus 12x plus 2? Right. Very good. So we've got our second derivative. And everything we do after this is going to feel like, didn't we already do that? And the answer is, yeah, we did. We just are going to do it with the second derivative now than when before we were doing it with the first derivative. So we're going to set it equal to 0. You can set this equal to 0 and solve it in one of two ways. Because there is only one x, that is a single term that has an x in it, you can move things around and take square roots and all of that if you'd like. It won't hurt anything. So I'll do that first, and then I'll show you what you would do in general when that's not the case second. So if I move my 12 to the other side, and then I divide by 12, x squared is equal to 1. What do I get when I take the square root? Yeah, positive or negative 1, right? Please remember square roots, positives, negatives. The other thing that we could do instead, if you prefer, is we could factor it. That is what we do in general when there's more than one term with x in it anyway. So we would take out our 12. I'd have x squared plus minus 1. And then we would factor using difference of squares. And we would still get x equals 1 and negative 1. Okay, so they're the same thing. We can do it either way because I only have one term with x in it. Is that good? Okay, I'm going to create a sign chart with those two values now. So the sign chart's going to have a value of negative 1 and a value of positive 1. I mentioned last time that sometimes we don't just leave these open-ended. We're having an interval that we're working on. Unless they specify an interval, which is usually happening in trig functions, we do leave them open-ended. It goes from negative infinity to infinity. If you think about this particular equation, it's a quartic, like power 4, right, polynomial. It does have, its domain is negative infinity to infinity, so it makes sense that this is open-ended. I need test points in each of these intervals. So something before negative 1. Negative 2. Between negative 1 and 1. 0. He's my friend anyway. And then how about after 1? 2. And again, you can choose anything. It doesn't mean it has to be these values, because all I really care about is the sign. And I want to look at the sign and the second derivative. So I'm going to be taking a look at this function and putting these values in. So if you want to grab your calculator so you can do it quickly, by all means go right ahead. If you want to just do it by hand or in your head, that's fine as well. I think I'm probably going to need mine later anyway, so I'm going to go ahead and get mine out. So we have 12x squared minus 12, and I'm evaluating at negative 2, 0, and 2. Okay, so when you put in negative 2, do you get a positive or a negative?
Positive.
Mine says positive. Does everybody say positive? Yeah? I'm getting some nods. Good. How about when you put in 0?
Negative.
That one's negative. And put in 2?
Positive.
Positive. So what does it mean? Well, positive means concave up. It means the graph's looking like that, right? Concave up means it sort of holds water. And if it's negative, it's concave down. So this is the image sort of that we're thinking in our mind when we're doing this. And we're going to report it back with those information pieces. So it's concave up from negative infinity to negative 1. And then from 1 to infinity. And then it's concave down from negative 1 to 1. It should just feel like same song, second verse. Right? I mean, it should. We did the exact same thing. We just took one extra derivative, right?
Will those tell us at the top of those concavity points?
It doesn't tell us concavity points. It tells us something else, and we'll get to what happens in between. Huh?
Our relative.
Nope. It doesn't tell us relative maxes and mins. We do have something related to this about relative maxes and mins, but it's not in the in-between points. Yeah, so we'll take a look at that. There is a relationship between relative maxes and mins and between the next thing, which is the inflection point. So suppose that we have a continuous interval, a function that's continuous on an interval, a, b, and the graph changes concavity. Ding, ding, we just did one, right? It changed concavity here at negative 1. It changed concavity at negative 2. So the previous example does exactly what this description is saying. It changes concavity. The graph is if the graph is concave down on one side, the graph is concave up on the other side, or vice versa. That's what the change in concavity would mean. And if that happens, the location where it changes concavity is called an inflection point. And let me just draw a picture of, roughly speaking, well, we'll just do an x cubed one, like this. About right here visually, it looks like it breaks. It's concave down right here, up until this, right? And after it, it's concave up. So the location where it changes concavity is called a point of inflection, or an inflection point. So you might imagine that what we just did before is pretty much how you find them, right? You look for places that the concavity changes. So you find the concavity, and that's exactly what you do. So if you're trying to find a point of inflection, A point of inflection always has one of two characteristics. It has a location where its second derivative is 0. That's what just happened on our previous example. Or it's a location where the second derivative doesn't exist. And we actually saw one of these last time as well. I'll draw the picture that we saw before. It looks like this. Do you remember that graph that we drew? When we talked about having a vertical tangent line? Yeah? Well, that location where it had that same vertical tangent line, it also changed to concavity, doesn't it? The graph is opening up over here, and it's opening down over here. And those positive and negatives are not increasing and decreasing marks, they're concavity marks. So while I didn't have a relative max or min there, I actually do have a point of inflection there. And the second derivative would not exist. In fact, the first derivative didn't exist on this one, which is why we had notated that there was a problem, so to speak, there. Okay? So if we're trying to find points of inflection, it feels a lot like what we just did in the last problem. We take the derivative, we take the second derivative, we set it equal to 0. We create a sign chart and we test for concavity, and if the concavity changes, we know we have a point of inflection. So it looks just like this over here with one step further. Now, we're going to do another one. It's a polynomial as well, and you have two choices on how you can do this. We're going to take a derivative, right? And it's a derivative of a what? It's a product rule with a chain inside. The chain's not very exciting, but it's there. Yeah. So you can do a product rule with this. If you don't want to do a product rule, you can multiply this all out, and that's okay too. Because it's a power of 3, that's probably not what I would choose to do, but if you wanted to, it's certainly possible. If you get to a power 4, at that point you're like done. You're not doing that, okay? So we're going to do a chain rule. We haven't done a chain rule and a product rule and a chain rule. We haven't done one in a few days, in fact, so we're going to do one on this one. So if I'm taking the product rule, remember I write the first piece down just like it is. And then I need a derivative of the second one. Okay, so I'm going to bring the 3 down. I'm going to rewrite the inside, and I'm going to decrease the power. Now, technically it is a chain rule, but I have already said twice, I think, that it's not a very exciting one. Because what's the derivative of the inside? 1. It's not very exciting. I'm going to write it just so that we say we did it, because we need to check, but this one just happens to be 1. And now I need the derivative of the first piece. What's the derivative of x? 1. And the second piece gets rewritten, x plus 4 cubed. Okay, this is the derivative. Again, you could multiply this out to do the second derivative. At the very least, you might want to clean it up a little bit before we do a second derivative, because it's kind of messy looking. So what does it look like to clean it up if I'm not going to multiply it out? Well, what you might notice is that some of these things repeat, right? There's an x plus 4, oh, minus 4, so sorry. That's supposed to say minus. Get that fixed. There's an x minus 4 in both pieces of what I've taken the derivative of, right? Like both parts of my derivative have x minus 4. In fact, there's at least 2 of them in each piece. One has 2 and one has 3. So what we could do is we could factor that out in front first. And in fact, that's a very nice thing to do. So I can take out an x minus 4 squared. And when I do that, I'm left with the other pieces. So namely, here, I'm left with a 3x. And what am I left with over here? An x minus 4. So right after the 3x, I have plus x minus 4. And I can clean that up or simplify the part that's in the brackets now and combine like terms. So I have now x minus 4 squared, and I have 4x minus 4. Okay? Again, if you want to multiply it all out, you certainly could. That's not an unreasonable thing to do at any point in this. But I want to show you some operations with factoring here, because it is kind of nice to do it that way too. Okay, that's just the first derivative, and we're supposed to be finding the second derivative, right? So we're going to keep going. Now I need the second derivative. All right, second derivative, I'm going to have chain rule, product rule, all that kind of stuff, just again like I did before. I'm going to write the first piece down, x minus 4 squared. What's the derivative of 4x minus 4? 4, yep. And now I'm going to do the derivative of the x minus 4 squared. So I'll bring the 2 down. I'll rewrite my x minus 4. It's got a power now of 1. Write it or don't write it, your choice. And the derivative of the inside would be, very exciting, 1 again. And then I have the 4x minus 4. Now once again, at this point, if you want to multiply it all out, even if you hadn't before, it certainly would be fine to do so. You only have powers of 2 at this point. It's not so bad. The same thing was actually kind of true up here, except that when we had a power of 2 times a power of 1, we would have had it messier. So if you want to multiply it out, you can. That will be fine. But I want to show you what it looks like if you choose to factor, because you can. Do you still see that there's an x minus 4 in each piece? Not an x minus 4 squared anymore, but an x minus 4. So this one has x minus 4 to the power 1, and this one has x minus 4 to the power 2. So I'm going to pull out the x minus 4 one more time. When I do that, there's still an x minus 4 left over here, and it's times 4, right? So if you want, and I will just this time only, I'll write x minus 4 times the 4 that's there. You could certainly multiply that out at that point. That'll be fine. Over here, I'm left with a 2 and a 4x minus 4. So this is plus 2, and then it's 4x minus 4. I'm going to put this in brackets just to separate it off a little bit better. Okay, a lot of cleanup needed on the inside there, but we can do that. We have 4x minus 16 plus 8x minus 8. Look okay? Combine some like terms, what do we get? 12x minus 24. You can certainly leave it as 12x minus 24 if it bothers you that the 12 and the 24 have a common factor and you want to take one step further and factor the 12 out, you could. It's not really going to help me at this point, so I'm just going to leave it, but it wouldn't hurt anything if you did. This is a very nice place for our second derivative to be, because I want my second derivative to be set equal to 0, right? So even if you had multiplied everything out from the very beginning or at some intermediate step in between, at the end of this, you're still going to have to factor it back out, right? You are, because the whole goal is to set it equal to 0, and you've got a quadratic at this point. So I need it factored. So setting each piece equal to 0. The first one is x equal 4. What's the second one? X equals 2. So either visually, maybe you can see it, 2 times 12 is the 24 minus the 24, or simply move the 24 divided by 12, whatever. It doesn't matter, either of those options. I have 2 values to put on my sign chart, 2 and 4. What can I test before my 2? 1 or 0. Kind of like 0, so I'm going to go 0, but 1 would be just fine. Between 2 and 4? We'll go 3. And after 4? 5. That'll work. Which version of the derivative, second derivative should you use? It shouldn't matter. I mean, it only matters if you've made some errors along the way. So you can pick whichever version of the second derivative you want to use. Either what we originally, I would probably go with what we originally came up with right here, or what we ended with down here. So pick whichever one of those you want to do and put that into your calculator. So I'm going to do where we ended. We're going to put in 0, 3, and 5. What signs do we get? Positive and then negative and positive. Okay, now the directions actually said to find the points of inflection and discuss the concavity. So I'm going to go ahead and do the concavity part first. We've already talked about how to do that because we did that once before. Positive looks like this, negative looks like this, and positive looks like this. So positive is the first piece is concave up. So it's concave up from negative infinity to 2, and then 4 to infinity. And then it's concave down from 2 to 4. Okay, with the exception of the processing of the derivative itself, that's exactly what we did on the first problem, right? It's all good? Yeah. We're supposed to also find the points of inflection. So there are 2 inflection points here. Anytime the concavity changes, I have an inflection point, as long as it's within the domain. And this domain, again, is negative infinity to infinity. I don't have any discontinuities. So I have inflection points, and they happen at the x values where the concavity changes. So my inflection points will be at 2 and at 4, but those are 2 points. So it's like this, 2, 4, like that. Now, it's not the point 2, 4. It's the point 2 something and 4 something. And I need to find out what the y value something is for 2 and 4. Where will I put the 2 and the 4 to find that? Yeah, Alex, you're right, in the original. So if I take my original, which was way back up at the beginning, x and x minus 4 cubed, that's where I plug in my 2 and my 4. So when I do that, the 2 gives me negative 16, and the 4 gives me 0. Which is interesting, because the 4 would have given me 0 down here too, right, if I did. But that's because that x minus 4 was a factor every step along the way, wasn't it? Yeah, that happened to stick around, and it stuck around because it was a power of 3, and it only took 2 derivatives. That's why it stuck around. But any questions on that processing? All right. We're going to come back to Daniel's question, which has something to do with extrema, relative max, relative min. There is a relationship between these second derivative pieces that we're doing and the relative max, relative min. Second derivative test, okay? So what we did before with finding second derivatives, making the sign chart, all of that stuff is not the second derivative test. Just like the first derivative test was not about finding increasing and decreasing. The first derivative test and the second derivative test are both about finding extrema. Relative max, relative min. Both of them are. But they're looking at it from different perspectives. The first derivative test is looking at it from the perspective of a first derivative, and the second derivative test from a second derivative. So it says the following: if we have a function where the derivative is 0 and the second derivative exists, okay, derivative is 0, second derivative exists. If the second derivative is negative, then we have a relative maximum. And if the second derivative is positive, we have a relative minimum. And this is what you were seeing happen when you were noticing second derivative being positive means that I would have a location like that, right? It does. And a second derivative being a decrease, or the second derivative being negative, being opening downward, means I would have a maximum. I just drew them backwards from where I wrote them. I did. Sorry. That's what happens when you zoom in too much. There's my pictures. They're in the right place now. The second derivative being negative is the first one. Opening downward has a maximum. And then the second derivative being positive, opening upward, has a minimum. So notice on here, it doesn't say anything about where the second derivative is 0, right? It's talking about the second derivative being positive and negative. However, it does say I need to know that the first derivative is 0. Agreed? So the only reason I'm finding second derivative here is to test what happens at those points where the first derivative is 0. So let's take a look at an example so you can see how it differs from what we did before. It says find all relative extrema, and then it says to use the second derivative test where applicable. We're going to do this by the second derivative test. So, according to the second derivative test, the first thing I need to do is find the first derivative and set it equal to 0. Okay? First derivative set equal to 0. So we're going to find the first derivative of a rational function this time. You have a couple of choices on how you want to do this. When you're looking at finding the derivative here, what could you do to find the derivative? Quotient rule. What else could you do?
You could move the x.
Not move the x to the top, because that would create a product rule, which isn't any different than the quotient rule. There's something else there.
X squared plus 2x and then 1 by x.
Yeah, you could do algebra simplification. So because the denominator is a simple single-termed creature, right, we could actually do this if you wish. I don't know that it's necessarily any easier to do one or the other, but it is another option, okay? Quotient rule is what we mentioned first, so we're going to start with quotient. We're going to do quotient rule. But if you wanted to do it, even as I'm doing the quotient rule with the simplification, by all means, you can do it that way too. It'll all work out. So I'm going to do it with the quotient rule. So we've got the denominator times the derivative of the numerator. So what's the derivative of x squared plus 1? 2x. And then we have our numerator, x squared plus 1, times the derivative of the denominator, and the derivative of the denominator is 1. And I have a sign error as soon as I said it, and I moved on. It should be a minus, sorry. Quotient rule has negative in between. Okay, and then it's written over the denominator squared. So it looks like this. Okay, so we're going to clean this up. I have 2x squared minus x squared minus 1 over x squared. And that gives me x squared minus 1 over x squared. So far, so good? Okay, so I need my second derivative to equal 0 when I'm doing this. That's what this says over here, right? I didn't mean second. I said second, and I'm using first. I need my first derivative to equal 0. That's what it says in the kind of the conditions at the beginning. So I have my first derivative. It's going to be set equal to 0. It will only equal 0 when the numerator equals 0, correct? Yeah. So I don't even need to test where the denominator is equal to 0, because that's going to be a place where I don't have the conditions met from over here. The conditions here do not say equals 0 or does not exist. Right? They just say equals 0. So I only need, in this case, for my numerator to equal 0. So where does x squared minus 1 equal 0? At plus or minus 1. Okay, we've already done this one today, but you could factor it or you could move the 1 in square root, right? Plus or minus 1. There are 2 locations where I may have relative extrema. And what the second derivative test says is take the second derivative and plug in negative 1 and 1. That's what it says. Instead of doing a sign chart, I can just take the second derivative, which I would have done anyway with the other method, and I would plug the values in. So I'm going to take the second derivative of my original function. So my second derivative here will involve the chain rule, or you can do algebra simplification again. I didn't mean chain rule, quotient rule. Or you can do algebra simplification, your choice. I'm going to continue to do the quotient rule since we've started that route. So my denominator times the derivative of the numerator, 2x, minus the numerator, x squared minus 1, times the derivative of the denominator, which is also 2x, divided by the denominator squared, which now gives me x to the 4th. Okay, so far so good? Yeah? All right, so we're going to simplify. I have 2x cubed minus 2x cubed minus 2x, sorry, plus 2x, divided by x to the 4th. Yes? Okay. The negative 2x cubes, they cancel. The positive 2x now, or the 2x on top is now positive, divided by an x to the 4th. But that will reduce to what?
2 over x cubed.
Yeah, 2 over x cubed. So we might as well reduce it, get it in its simplest form. So this is my second derivative. And what I need to do is I need to take these values from my first derivative and evaluate. So I do my second derivative at negative 1 and my second derivative at positive 1. I don't think I need to put it in my calculator, so I'm not going to. What happens when I put 1 into, or we'll start with negative 1 since I listed it first. Negative 1 into 2 over x cubed. It's negative. And what happens when I put in positive 1?
2.
It's positive 2, right? It's 2. So it's positive. It's negative, it's positive. Well, these are second derivatives. Negative means concave down. Positive means concave up. That's what it means. So if it is concave down, do I have a max or a min?
No.
I have a max, right? There's a visual picture that goes with it. And if it's concave up, I have a min. So I have a relative max at, and the x value is negative 1, but I still need to find the y value here in a minute, which I will. And I have a relative min at a positive 1. Okay, so just like when I'm finding any other relative max min or inflection point, I will do what in order to find the actual location of y? Yeah, I plug it into the original. Man, I'm trying to move this over. You know what? We'll do that. The whole thing's moving. Okay. So I'm going to plug it into the original. And in the original graph, up here, if you want to do it again by hand, by all means do it by hand. If you want to use your calculator, use your calculator. We're plugging in 1 and negative 1. They aren't very hard things to plug in. What happens when you plug in negative 1? Negative 2. And if you plug in positive 1, you get a 2. So this is my relative max min. Sometimes I feel like when I do the trig examples, it's like Sunday morning when your worship minister puts that token hymn in. Y'all know what I'm talking about? It's not really like that, but it kind of feels that way. We need to do something with trig because trig works a little differently when we're working on these. And then typically it has intervals, which we see happening here, right? 0 to 4 pi. All right, so the directions are much the same. We're using the second derivative test. We're trying to find relative max and min. So we have a function on this one that's actually a sine function. So I need to find the first derivative and set it equal to 0. So what is the derivative of sine of x over 2? Okay, so the sine becomes cosine of x over 2, and then the derivative of the x over 2 is 1/2. Okay? It's a chain rule. It's not a very exciting chain rule, but maybe it's a little more exciting than the last chain rule because the derivative isn't just 1 on the inside. It's actually 1/2. Sound good? Okay. I'm going to set that equal to 0. Well, that's unit circle stuff, and I've got to go clear out to 4 pi. It's going to feel kind of funny what I do just a moment here, but you'll see how it's going to work itself out in the end. So on the unit circle, where do I have cosine values that are 0?
Pi over 2, 3 pi.
Yeah. So it's at the top and at the bottom of my unit circle. Remember, cosine are the x values. Those x values are 0. So I have pi over 2 and I have 3 pi over 2. It feels like, oops, I didn't mean to put that there. I should probably mention this. The 1/2 here doesn't matter when I'm setting this equal to 0. If I were to multiply by 2, I really just have the cosine of x over 2 equal to 0, right? Everybody good with that? The 1/2 didn't affect it? Okay. So I want my angle measure, that is my x over 2, to equal those values. So I have pi over 2 and I have 3 pi over 2. Now, in theory, it feels like you should just continue to go around, right? I'm supposed to go to 4 pi. If we continue this, I will have 5 pi over 2 and 7 pi over 2. They're not going to be necessary, but it feels like we should write them down because they're between 0 and 4 pi. Does that make sense? Right? It would go twice around my unit circle. The reason I don't need to write them down is because I'm about to multiply these by 2, right? I'm solving for x. And when I multiply all of these by 2, I'll get x equal what?
Pi, 3 pi, 5 pi, and 7
Pi, 3 pi, 5 pi, and 7 pi. And what do you notice about the 5 pi and the 7 pi?
So 4 pi.
Yeah, they're no longer inside of our interval, right? So the reason that they set the interval to go from 0 to 4 pi was to capture a full unit circle once we multiplied by 2. That's why they did that. So it really is enough that we did a full rotation, and if we had failed to sort of think through, oh, maybe I should put the 5 pi over 2 and the 7 pi over 2, it wouldn't have hurt anything. Because they're going to be eliminated at this point anyway, because they're no longer between 0 and 4 pi. All good? Okay. These are the two values that at the very end, like over here, I'm going to test inside of the second derivative. I'm going to test pi and I'm going to test 3 pi. But in order to get to that point, I now need to find the second derivative. So we're going to do that. Our second derivative. All right, so I need the derivative of 1/2 cosine of x over 2. What's that going to be? Okay, so I know you're really good at pushing them all together, but I'm going to take one. You're fine. Don't apologize. It's great. So the derivative of cosine is negative sine, so it's going to be negative. And there's a 1/2 there already, but then I need the derivative of the 1/2 on the inside, so I'm going to get 2 1/2s. So I'm going to get a 1/4. So everybody see where all the pieces came from? I merged them all together at one time. If you need to see them written out in more than one step, by all means do that. We're all good? Okay. There's really nothing to simplify, right? I don't have any algebra or trig to combine or anything on this, and this is lovely. You guys all think that trig is sometimes not your favorite, but this is actually very nice on this one. And I want to take these two x values, that is pi and 3 pi, and I want to put them into the second derivative. That's what the second derivative test says. It says to use the second derivative to evaluate those locations where the first derivative is 0. So I need to find f double prime of pi and f double prime of 3 pi. And I'm going to write them out on this one because it is trig. So, oops, that's 1/4. Negative 1/4. I have the sine of, and it's pi over 2 now. And then I have negative 1/4. And I have the sine of 3 pi over 2. My unit circle happens to still match this picture. 3 pi over 2 and pi over 2 are the pictured pieces. What is the sine value at pi over 2? 1. So this is negative 1/4 times 1, or simply negative 1/4, right? And in particular, it's negative. That's the important part. What about the sine of 3 pi over 2? It's negative 1. So I have a negative 1/4 now times negative 1. The negatives cancel. This gives me a positive 1/4, or in particular, again, I care about the fact that it's positive. What does a negative second derivative mean? It means it's concave down, and it means I have a max. You're right. And if it's a positive second derivative, concave up and a min. Right? So I have a relative max at pi something, and I have a relative min at 3 pi and something. So how do I find something? That is the somethings I referenced. How do I find it? Back in the very original, right? It's always going back to the original when we're reporting our answers at the end. So I'm going back up here to the sine of pi, the sine of x over 2. So I need the sine of pi over 2, and I need the sine of 3 pi over 2, which we've already talked about because it showed up in the second derivative. What was the sine of pi over 2? 1. And 3 pi over 2? Negative 1. So this one's 1, and this one's negative 1. All right. Any questions on that? Okay. We do have a quiz over this section in the previous one, but it is set for Wednesday next week. It will stay on Wednesday. So we'll leave everything just like it's showing up in the schedule, okay? We'll just shift our sections around a little bit since we're a tiny bit ahead. But no due dates.